Hello everyone, welcome to the second video on simplifying quantum computing or understanding basically, which I call it as thinking beyond bits, right? So there are a series of videos that I planned. So this is the second video. So I will just try to talk on 3-4 points that I write daily in smaller videos. Yesterday, hope you have seen the video one where we just spoke an overview about what quantum computing is, how it evolved, etc. So there are a few calls that I got saying that this served them as a good audio transit. So when they were driving, etc. So these kind of things. I'm happy about that. So second day, let us discuss about why classical computers are limited, right? So because we thought of doing it as a series, I wrote 4 points for today, so you will get an understanding of what it is, so you don't have to refer or repeat it again. So if you just follow it through, just like uh, easy to go, easy to take type, so I think you will get a fair understanding, right? So now, for the benefit of everybody, because I have seen mix of people viewing it, like students and early professionals, also the seasoned professionals who called me, couple of guys. So I just try to keep the tone very balanced, so so that everybody gets a benefit out of it. Right now, coming into the topic, so I just try to cover in few minutes, maybe 7-8 minutes for today, why classical computers are limited basically, right? If you understand this, so then why quantum computing is needed, we will get a fair idea. So we often hear statements, right? Computers are extremely powerful, so which we all agree, and there is also a term which is supercomputer, so which they say they can do trillions of calculations per second, which is also true. But while all of this is true, but the less discussed fact is that even the most powerful computers or machines in the world have got serious limitations, right? So not because they are technologically weak or they are designed that way. Simple answer is that they are designed for specific use cases. So if you understand, or if you just think and reflect, right? Classical computers or traditional computing are excellent at tasks like doing calculations, or if you want to store data at a basic level, and some instructions, if given to them, they follow and execute them very meticulously, repeated steps accurately, right? So if there are 1 2 3 4 5 steps given, so they will say step 1 done, then I'm going to step 2, step 3, step 4, step 4, like your if else condition or whatever, right? So this is extremely fast, because uh, when you compare manual work with automated, so these classical computers are very very fast, no doubt about it. But this approach works for certain use cases only. Say, like if you talk from the industry aspect, good for accounting, good for what do we say, word processing, for browsing, right? And for your, if I have to play back my video, all these things on a laptop, so which is working fine. Basically, pretty much my everyday tasks, whatever I do, is pretty good at it, right? So now, when the problem becomes too large, now if you understand what is this large problem that we are talking about. So imagine yesterday we discussed about some route optimization thing, right? So there is one. Now let us simplify it further and then say, if I own 100 delivery vehicles, for example, and there are 1,000 delivery locations that I operate day in day out, and I have certain constraints, right? By the end of the day, as a businessman, I will look at optimizing my fuel, my traffic, I mean the route optimization, all these priorities will come into picture, right? So the number of possible schedules is huge. When I meant huge, the from a scheduling aspect, right? So the permutations and combinations, so which route to take, so which route got less traffic, etc., etc. All these things are optimization techniques that probably we use it, right? Now coming back to the classical computer aspect, so what it does, it will try the schedule number one and then check whether if it is good or not based on my constraints or limitations or the checkpoints that I have kept. Then and if it is good, then it is go to the another schedule, check it, compare, so then gives me the best. So I mean this comparison happens after 1 2 3 4 5. Now this happens at extreme speed, no doubt about it, but the problem is not the speed, it's about the permutations and combinations, and this exploration, whatever we are talking about, is the actual problem, right? Now it immediately comes to our mind that if the computers are slow or if the permutations and combinations are more, why can't we make our classical computer faster, right? But it's not the issue is not about the speed. Issue is about the exponential behavior, right? Exponential way of doing it. Suppose if I have 110 possibilities, then it is easy for me to manage. If it is 100 possibilities, yes, okay, I can compare still after 1 2 3 4 5, and then do that. If there are 1,000, I might take 10 minutes, 20 minutes, and then probably that comparison can happen whatever time it takes. If there are 100,000 possibilities, 100,000 is 1 lakh, so then slowly you might see that kind of a hit, right? Speed, when it is increased, we are increasing it linearly. When I meant linear, linearity is 1 2 3 4 first step. After 1 2 happens sequentially, right? At some point of time, say as the number of possibilities are increasing, we are hitting the wall, right? So at certain point of time, if it is 10 lakhs or 1 million, you are hitting the hard wall, for example, right? So like this. Now let us come back to some 2 3 real world examples that I wrote, right, from science and technology aspect, which you will all be able to relate, and then if you want more you can google and then check further on those kind of things, right? So if from a science aspect, if simulating molecules requires some accuracy, right? And then how many particles are there, classical computers work on a way, something called approximation. But what we need here is not approximation, because from these kind of use cases, approximations fail when the molecules become more complex, right? So this is what they say. Now this is about the simulation case. Now coming back to the optimization problem, say like the logistics, the supply chains, the route optimization, and all these kinds of stuff. So then classical computers struggle. That's what we have seen, right? Briefly discussed. Now imagine the weather systems. If you has to go back, compare, and all those things. So this is also this. I mean, we are talking about highly interconnected comparisons that are happening. Suppose a delivery vehicle need to go from A to B. So what is the weather right now? What is the traffic real time? And then any other plan B route. All these kind of things should happen real time. So then classical computers, there is every possibility that it might struggle after certain exploration, this thing, right? Possibilities. Now I will not say they become inefficient, but there is certain struggle for certain that is foreseen, right? So now, this doesn't mean, I just reiterate, classical computers are not going away or going away, right? So they will stay, but I will also not say it is outdated. So tomorrow somebody says AI is everything and then the manual thing is gone. No, when it comes to creativity, you still have to prompt, you still have to think, you still have to do many other things. So to utilize it as a good assistant. Likewise, classical computing will still continue to stay. It is not outdated, but it it is it does not also mean that everything moves to quantum computing tomorrow morning, right? As I mentioned, it is based on the use case, right? So, to run our phones, to run our businesses, small and medium, to run our daily lives, we don't need quantum computing. Let us be very clear, right? So, quantum computing is not a replacement. So, it is a complement. You have to understand these two keywords: replacement versus complement. Quantum computing is not a replacement, it's just a complement for what it is available today, right? Uh, to be specific, it is designed, or uh, it emerged to help only where classical computing struggles, basically, right? So now we know, yesterday also I mentioned in the video, right? Calculator has its own use, so we will not use it for a different purpose. Microscope has a different use, and your camera has got a different use. So likewise, so now, uh, why this limitation led to quantum computing? So this is the important question that we need to reflect. So before we get on to the deeper aspects of quantum computing, so when somebody faced these problems, especially when I meant who are, say, scientists, right? So when they face these hard problems, so they might have thought, what if we force the computers to think step by step, right? So once this linearity is gone, so what if we guide them naturally, right? As if that nature guides computation, something like that. This is what they say. So going forward, we will try to connect those dots as well, but as of now. But again, it is not a shortcut, not a magic, but these are the kind of questions that uh, uh, from these questions the concept of quantum computing emerged, right? So now, when this fresh new thinking, new representations, these computational approaches, so will help us uh, uh, get away or get out of these limitations of classical computing, right? So, first of all, slowly reflect why quantum computing exists at all, right? So, these are the questions that we should reflect at least for 30 to 50 seconds or 1 minute or whatever. Just think so that our understanding becomes deeper. So, now, before we get on to next video, and then we understand what are bits versus qubits that I mentioned. So reflect on this question, why quantum computing exists at all. So I think in the next video when we meet, we will slowly go deeper and deeper and then try to understand better. Thank you very much for listening and viewing this video. We will meet in video 3 with a better and interesting topic. Thank you very much.